maybe we should think about starting. It was at 1 sharp. So I would like to say welcome to everyone. And I'm Patron. I'm part of the faculty at this division. So I'm going to be the chairman for this session. So I will start by just saying a couple of words of what will happen. And then we'll turn to the real procedure. So we are, of course, happy today to have the public defense of Vidar Aspelin. And this will be the defense of this thesis, modeling of inorganic ions in aqueous solutions. And the procedure today is that we will start with some presentations of the science, first by the opponent, and then a little bit followed up by Vidar, the respondent. And after that, there will be questions, mainly from we have a committee that is supposed to evaluate this. And after that, we will open up more generally to the public. And so you know, the first presentations, we will have a very short break in between after the presentations if someone needs to get out.
Just press one of these. So
oh, this is green. It should be on.
yes, now the people in the audience outside electronically, they will see you as well.
Ah, okay.
Yeah, it's now zoomed out. So
okay, sorry. Of course, yes, and then of course we are happy to be able to do this in person mainly, but we also have some presence online over Zoom. So you will see this. I will, before I hand the word over, I would like to present the main people involved in this. And then first we have the respondent, Vidar, who is defending his thesis, his work that he's been doing for several years. Then we have a faculty opponent, the person who will ask questions. And this is David van der Spoel from biology in Uppsala University. And I can't see him, but I hope we have David here online.
Should be here, yes.
Yes, I'm here.
And we know that there were some last minute rearrangements, so we're very happy that you could step in and do this. And we're sorry to not have you here in Lund, but we're happy to see you connected from Uppsala. So very
It's a
welcome.
pleasure. Thank you.
Okay. Then we have a committee, and we have one external member. We have Rina Krarup Thand, and she is also online. So she should also be here on.
Yes, I'm hiding here behind you.
Okay, so very welcome to you too.
Thank you very much.
You are at Copenhagen University. So we welcome you very much. And then we have here locally in Lund, we have from the Department of Theoretical Astronomy and Theoretical Physics, or biophysics. There is computational biophysics. There is Tobias Ambjörnsson. And then very locally from our neighbors, good neighbors, from physical chemistry, we have Joachim Stenhammer, who is also, well, from the chemistry center here. So these are the people with official duties today. We should also mention we have Mikael Lund, who is in the audience, who is the supervisor of Vidar. So I think you have to sit and look at this, but of course you have played an important role throughout the process of getting here. And with this, I would say that we can start. And then I would first ask you if you have anything to add or that you want to add or change as we start this thing.
There's 2 errors that I found when I read through it after printing, and that's on page 15. There's a miscalculation for the total multiplicity, and in section 7.2, the free energy referred to as F should actually be referred to as A to correspond to the previous notation. So section 7.2 is the one Bennett's acceptance ratio. Yeah.
Okay. And with that, I think that we then hand over the word to our faculty opponent, Professor David van der Spoel from Uppsala University, as said. So, David, please, if you would like to start with the presentation on the scientific part.
Yes, thank you very much. then as one does these days, I will share my screen and start a presentation. Can you see that? I guess you can. All right, so it's my pleasure to be the faculty opponent for the defense by Vidar Aspelin, modeling of inorganic ions in aqueous solution. And here we have the cover of the thesis. I guess you have all seen it. And I have worked a bit in this field myself, and there will be plenty of questions and good discussion, I hope. So first, I want to congratulate Vidar on writing a very comprehensive thesis. The introductory part is really good. I liked it a lot. But of course, there's always room for questions. So to put things into context, it's important to ask ourselves the question, why would we be interested in inorganic ions in aqueous solution? Well, I guess most of us, when we make pasta, we put some sodium chloride in the boiling water. So we realize that it has some kind of function to play, but in daily life. But there is actually much more. So what is interesting about inorganic ions in water? Well, in fact, the behavior of those ions in water and any molecule, as a matter of fact, is rather complex, and it's not really completely understood. There are many observations that one can make in the lab or in practical life, as I mentioned, where ions come into play. And so one such example is in atmospheric chemistry. So droplets of water in the atmosphere that come from the ocean, they take with them salt, and that has an effect on, for instance, ozone depletion. And as we know, ozone is very important to protect our planet against radiation. So this kind of balancing reactions with ozone creation and depletion are very important for our daily life. Ions are also important in biology, and although Vidar hasn't really worked in biology in this thesis anyway, it's still important to note that the difference between, for instance, sodium and potassium ions is really important for instance, signal transmission in neurons. But we'll not go into that here, so we'll focus on rather simpler systems. So let me give you an example. So here we have a picture of the ocean, and you see there are waves, and those waves splatter. So water evaporates and condenses. And when droplets evaporate, or where droplets are released from the water, they take with them basically everything that's in there. And that can be organic compounds. If you go to the beach, especially on the West Coast, you find that seawater has this characteristic smell of dimethyl sulfide. But there are also ions, and this is, of course, the chloride and bromide are among the simplest ones. But this is the work that Vidar has done, where he has studied those ions. And now, if those droplets become really small, then we find one of the first important strange observations, that those ions which are charged, so they should actually be well soluble, they actually move to the surface. And here we have made a zoom into one of those droplets, and of course we can make such nice zoom in pictures in computers. It would be a bit harder to make like a real atomic picture, but so here we have a droplet of a couple hundred water molecules, and then the bromide ion is situated on the surface here. And what we can do in a computer is we can take such a bromide ion and move it into the droplet, and then measure the energy that it takes to do this. And from that, we can learn something about how different ions behave. And And Vidar has done similar calculations where he looked at also surface properties of different ions in paper 1. We also find that also hydronium moves to the surface of droplets, but not hydroxide. And organic compounds do that as well. Even things like methanol and ethanol, which are completely soluble in water, if they have a chance to go to a surface, they will, in particular in small droplets. And the simulations can help us to make sense of these things. So here we have again our droplet with a bromide ion. And if we now look from the center of the droplet to the surface, we can basically slowly pull the ion out and measure the energy or the force on the droplet. And from the force, we can calculate the energy. And then we see here in this inset of this little plot that from a distance of 0 to the surface of the droplet, the energy goes down. So we see that for the heavier, the larger the ion, the lower the energy is. So that means that in this system, which is still rather simple, we can explain why the ions go to the surface preferentially. And as I mentioned, Vidar has looked at some of those things in paper 1, for instance. Here's the surface tension of water ion solution as a function of ion concentration. And we'll get back to that in the questions later on. But simulations, they can give us many answers, but they are not without problems. And simulations are always approximations. And within these approximations, we have to consider that that sometimes there are errors and we need to make methods that take into account the proper physics in order to be able to get good results. If we don't, we might up with something like this, simulation artifacts in pure water. So here you see a picture and you have to look a bit close of 2 boxes with water. Both of them have some kind of layering. And you see the hydrogens in white and the oxygens in red. And you see basically that there are 4 layers in this box, which are more or less perpendicular to this axis. And in the other box, we also have 4 layers or slightly more, but they are at an angle. So this was a paper that was published 2005 or so by a Japanese researcher. And then my group started looking into that and we tried to figure out what was going on. And it turns out that Vidar has also looked into these things, but maybe from a slightly different perspective. So this is an image from paper 2, a figure. And what we see here is in a box of water, how the water molecules align with each other as a function of distance. And if we look here, for instance, we see that a peak of the dipole of the water molecule at a certain origin, so at 0 compared to the dipole at a certain distance. And what one expects at short distance, there is a peak in this function, which shows that the 2 molecules are strongly correlated. So they are sitting next to each other, they form a strong interaction, and therefore the orientation of these water molecules is really correlated. And then if you go further away, then the interaction between the 2 molecules is of course shielded by other water molecules. And then at infinity, there should basically not be any such correlation anymore. Now the question is, how well can we model that? So there are different methods, and in this case, the Ewald method, which I cannot explain for lack of time, but that is basically the standard that everyone uses. So in this case, the dark line is the one that goes to 0 relatively quickly and then remains 0. So that means that for from a distance of like 1.1, 1.2 nanometer onwards, there is no interaction between those water molecules anymore. And now Vidar has made, together with other researchers in the group, a model to approximate this this reference method. And basically what you see is that depending on the level of approximation, there are artifacts that are related to where we put the boundary cutoff in this method. So the approximation works in a way that one assumes that there are no interactions beyond a certain distance. And depending on where you put the distance, the further you put this distance, the better the approximation becomes, which you can see from that the peaks here are higher than here and even higher than here. But also the further you put out this cutoff distance, RC, the more expensive this calculation becomes. But anyway, so there are these artifacts in the simplest form of the approximation, and they become better if the approximation goes to higher levels. But this is one of the things that I will discuss with Vidar a bit later. Now this looks very familiar to me because I published similar figures a while ago with similar models, and there the model that most looks like Vidar's model is called a switch function, and we also have this Ewald model, and then a couple of other models. And these cutoff artifacts, they reappear in most of those different methods. And so I call them red and green and yellow to say how good they are. Now, even though this one looks a lot like Vidar's model, it should still be considered that actually here is a series of models in Vidar's papers. And there are different degrees of, well, at the highest level of approximation, most of these artifacts go away actually. But the thing is with these simplified models is that if you apply them to a simple case like pure water, then everything is more or less easy to control. But if you have a more complex case, it becomes more difficult to maintain that actually. So here is a paper with a similar, not entirely the same, but a similar method, which also assumes that there are no interactions beyond a certain cutoff. And in this case, it was tested on liquid crystals. And what these authors find is that the energy of a crystal as a function of temperature is plotted here. And you see two lines because there are two different phases. And the Ewald method is more or less on a straight line and reproduces both phases. But the approximate method more or less breaks down in the middle and it becomes somewhat of a mixture between the two. So in order to evaluate such simplifications, it would really be necessary to look at more complex systems. And I must say I'm rather skeptical about these things. I don't believe in silver bullets, but some people do. And I think we can discuss more later. So let's move on to paper 3. And this is a combined experimental and theoretical paper, which is really commendable. One often gets more insights when one combines different methods, especially experiments. I think they are needed to keep us theoreticians with our feet on the ground, because we cannot explain everything with our models yet. On the other hand, interpretation of experiments is also very tricky, and that often requires models. This was a rather complex paper, and I have some detailed questions later, but I will be happy to hear more, more explanation of, for instance, the modeling of the experimental data. And the paper is about binding of potassium ions to crown ethers. That was a bit of a surprise to read about crown ethers. I haven't really followed that, but supramolecular chemistry, there's this kind of complexes. They were rather popular in the 1990s, and Nobel Prize was given to Jean-Marie Lane for this work. And they are, of course, still useful as model systems. I'm sure they're also used in applications, but as I said, I haven't really followed that since a long time ago. And so one of the intriguing things that comes from this paper is the suggestion that potassium ions attract each other in solvent. So yeah, this we will really have to discuss, because maybe I misinterpreted that. Whether this suggestion is or this conclusion in the paper, which is also highlighted in the abstract, that potassium ions attract each other, really is only based on the continuum electrostatics, or whether there is empirical evidence from that as well. So look forward to that discussion as well. Then, unfortunately, I did not have enough time to prepare questions about paper 4, so I hope that the committee has some to fill in there. And then I can just summarize this introduction. So I would like to repeat that air and water systems are important in many fields of science, from anything atmospheric chemistry to biology and many other applications. And theoretical methods can help to explain complex phenomena. They can often yield like detailed molecular insight, but it's of course, it is important that we benchmark those methods to experimental data wherever possible. And Vidar has worked on both applications and method development, and he was also, as I understand it, instrumental in the experimental work, which is very nice. And my conclusion is that I think some theoretical methods are more helpful than others. And maybe at the end of our discussion, we can agree on some things. And if not, we can disagree and part as friends as well, I hope. So with that, I would like to end my presentation and pass the word to Vidar.
Okay, so let's just say thank you very much, David, for this nice introduction. And of course, we look forward. We see that you've set up the stage for many interesting questions. And with that, we turn to the presentation of Vidar.
Sorry, I cannot hear you.
Mm. Så. Nu.
Now
Okay.
it's better.
Yeah.
Thanks.
Okay, thank you. Is it good volume out? Yeah. Perfect. Okay, thank you for coming to this defense of my thesis entitled Modeling of Inorganic Ions in Aqueous Solution. So I'll just first briefly go through the outline of this presentation. I'll start with talking, as David also talked quite something about the relevance of inorganic ions. Where do we find them? Specifically about one weakly hydrated anion that we studied, and why we need simulations at all. Why don't we just settle with experiments? Some method development that we studied in one of the papers, and finally another benefit with simulations, which is that you can often explain counterintuitive experimental results, which is not possible to explain from the experiments themselves. So where do we find inorganic ions? As already mentioned, the iodide ion can be found in the ocean, and at the surface of the oceans, these ions participate in ozone depletion, which ultimately affects climate and air quality. In the human body, we find the sodium and potassium ions in this sodium-potassium pump, which is responsible for, among other functions, transmitting nerve signals in our body. And overall, ions are very important in solutions because they alter the electric environment and affect how other solvated molecules interact. And they are all carrying a net charge, so that means that they interact on a long range. So it's important to understand what makes up the difference between different ions, for instance. So one way to rank different ions according to the properties was done by Hofmeister in the 19th century, where we ranked different anions according to their ability to increase protein structure stability. And that means that ions to the very left here increase the surface tension of the solution also, and they salt out proteins, which means that they decrease the solubility of proteins. Whereas on the other end, we see the opposite, so decrease of surface tension and increase of protein solubility. And on the very extreme end here, we find this thiocyanate anion, which shows these properties to a large extent. So what is it then that makes up their unique properties? I mean, these are just charged particles, you might think, but still they're very different. They behave very differently. So if we pick up 4 halide ions from this Hofmeister series plus the thiocyanate ion, we see that they all carry 1 negative charge, right? So in the very simplest model, we might just say, okay, we just put 1 minus charge and we model them as that. But we know from experiments that they behave very differently. So what about their size and what about their polarizability? How mobile the electrons are? This is what is done in all atom simulations. We give these ions other parameters than the charges, and the total set of parameters is referred to as the force field. The force field we feed into the all atom simulations, which allows us to study these atoms on a very fine detail. So just to give some context of where all atom simulations come into the general picture of our study of chemistry, here I show you a map where we have the time scale. So at what time scale does the phenomena we're interested in happening on, and also the system size. So the very most detailed studies we have, or methods, is quantum mechanics. In quantum mechanics, we study the electrons and the mechanisms underlying reactions between molecules. We can make it a little bit simpler to represent several atoms as a single entity in coarse-grained simulations, with the benefit that we can simulate for a longer time and also larger systems.
but we lose some detail because we simplify the system. In even more coarse-grained model, we can refer to as macroscopic methods. We can, for instance, study transport phenomena of even larger particles like bacteria. And in the middle here between coarse-grained and quantum mechanics, we find all atom simulations, which serves as a very good model to study, for instance, ions and smaller molecules. So this has been the focus of my thesis and the development of force fields. And the problem with we realized that all these 4 ions to the left here, there were already very good force field describing these ions. But for the thiocyanate ion, it was lacking a thermodynamically consistent force field. So we decided to try to develop such a force field where we managed to reproduce properties on both the air-water interface, which is important since thiocyanate is a very surface-active molecule, and also in bulk solutions. We looked at some bulk properties, such as the bulk solution structure. So here you see the probability distributions of the cations around the thiocyanate. So we studied 2 salts, sodium thiocyanate and potassium thiocyanate, and the green one is for sodium thiocyanate, and the blue one is for potassium salt. And as you can see, the potassium ion actually forms a diffuse first coordination shell around the whole molecule, with a slight preference for the sulfur atom, whereas the sodium ion the distribution is more localized to the nitrogen atom, with a strong preference for the nitrogen atom. And we can also distinguish a third solvation shell in the sodium salt, which is not readily present for the potassium salt. And this turned out to have implications for the formation of clusters in solution. So the stronger interaction between sodium and the nitrogen atom resulted in larger clusters, which had more globular shapes, were more closely packed, whereas the weaker interaction between sulfur and potassium resulted in smaller clusters, which were more linearly stacked. We also looked at properties at the air-water interface, and first we validated against experiments by computing excess surface tensions. And then we also looked at the behavior of the thiocyanate at the air-water interface, and we saw that comparing to a previously developed force field, that the angle to the air-water interface was very different. So in our force field, we got the most probable angle of 50 degrees compared to almost parallel in the previous force field. And this result was more in line with another study that had been done before using ab initio molecular dynamics simulations. So one very important type of interaction when studying ions is the electrostatic interaction due to the fact that they carry a net charge. So this is the interaction between charges, fixed charges in space, and it is long range and decays with 1/r. So this is the expression where the Qi and Qj are the charges on 2 atoms, I and J. And then we have the relative dielectric constants epsilon r, vacuum permittivity is epsilon 0, and then we have the distance r between the atoms. So the problem here is that in simulations it's quite expensive to simulate all atom simulations, so we can't make the system very large. We can't make it as large as we have typical samples we have in experiments. So typically we simulate quite small systems, but this interaction is long range. And if we just evaluate this interaction within a small box, we'll get a large error because the potential diverges outside of this region. So the normal way to solve this problem is using the standard method that was already mentioned, also Ewald summation with periodic boundary conditions. And what you do is that you replicate the system. So we have the it's a little bit poorly visualized here, but the black box in the middle is the simulated system. And then you have a more gray color, which are the replicas of this cell. And what you do is that you replicate this initial simulated system, and then you split up the interaction into a long-range part and a short-range part. So within this white cutoff, you evaluate the short-ranged part of the potential, and then you also have the reciprocal space part, which takes into account the interactions with all the neighboring cells. The problem with this, the problem is can be for large systems and for complex systems, is that it is very expensive, and it scales very fast with number of particles. So the question is do we need this quite expensive method? Can we reduce the simulation time by introducing a more efficient potential? So it had been shown that if you cut off the potential at a certain distance, it has been shown that the truncation error on the energy is actually proportional to the net charge of the cutoff region. So that sort of implies that we can actually correct for this error. And this was the starting point for the development of a potential where we simulate a system, and then instead of replicating the system in a large lattice, we correct for the fact that we are truncating the interaction. And then the idea is that the sum of those, the correction and the real simulation part, should approximately be the exact result. With the great benefit that it would scale much better than Ewald. It would scale with number of particles n rather than n to the power of 3/2, or n log n, as will Ewald and particle mesh Ewald. So this was, we call the Q potential, which cancels an arbitrary number of electrostatic moments, which we call P at the cutoff. Also cancels P-1 derivatives of the potential at the cutoff. And it only requires 2 input parameters, which is the cutoff distance and the number of moments to cancel. And in order to sort of test this potential, how good did it perform, we compared it to 4 other potentials, 2 other short-range potentials, where one cancels 1 derivative at cutoff and the other 3 derivatives, and also to the standard methods, particle mesh Ewald and Ewald. We looked at pure water and aqueous salt solutions, and we simulated these systems with different cutoffs and number of cancelled moments. And we calculated a range of properties such as radial distribution functions, solution densities, and diffusion coefficients. So here we show, here I show you the radial distribution function, which is between the water, oxygen, and salt, which is GOC, as a function of R. That function -1, and then scale with the Jacobian. So this tells us something about the solution structure. And the black curve is the result from particle mesh Ewald, and then we plot the other potentials on top of that. So we can see that the blue curve is corresponding to the lowest value of P that we tried, that we only canceled 2 moments at cutoff, which performs quite poorly. It shows large errors compared to particle mesh Ewald. If we increase the number of moments to cancel to 3, 5, or 7, we get instantly much better results. And also interestingly, if we increase it even more to approach infinity, we actually get worse results again. So somewhere in the middle seems like the best choice. And whereas the short range potential that only cancelled 1 derivative at the potential is quite poor, the one that cancels 3 behaves very well as well. So if we choose these input parameters appropriately, we get results that agrees well with the standard methods. And for the shortest cutoff tested, the optimal choice is quite narrow. But if we increase the cutoff, the optimal range widens. So yeah, I'll just take a step back now and again explain why we need simulations. So we have, first of all, experiments. We go in and measure in the lab some sample that we think is interesting, some molecules, and then which of course adds to our knowledge. from our knowledge, we can form theories which more in general describes the behavior of atoms. And these theories can be very simple or very complicated. And using these theories, we have been able to develop these tools for molecular simulation, which is great because now we can actually study much larger systems of tens to hundreds of thousands of particles, which would be impossible to do with pen and paper. So we can gain a lot more information using molecular simulation. Still, we of course need these experiments because we have to calculate, we have to compare some property calculated in simulations to experiments to ensure that we have a model that's actually somewhat close to reality. On the other hand, we can also use simulations as preliminary work. If we know that we have a decent model for some molecules, we can sort of extrapolate and simulate other molecules and get information of where we should start in this design of a certain molecule with a specific property, for instance. And we can also explain counterintuitive results in experiments, which was a major focus in the third paper, where we looked at a molecule consisting of one crown eater. So crown eaters was discovered in the 60s, which gave a Nobel Prize due to their unique capability to strongly bind cations of different size. So depending on how large you make these molecules, you preferentially target a specific ion. We studied a molecule consisting of two of these molecules, where we saw through isothermal titration calorimetry experiments that the binding of a second potassium ion to this complex yielded a larger heat than that of the first. So the enthalpy of binding of the second one was less negative than that of the first, or sorry, more negative than that of the first. And at a first glance, this seemed counterintuitive because using the Coulomb equation, we see that if we have two charges of the same sign, these charges repel each other actually. So this would mean that it's very unfavorable for these ions to come close together. But in these experiments, we saw that when we fix both ions in the binding sites, it was favorable from an enthalpic point of view. So in order to, as a first step to explain this, we turn to continuum electrostatics, which is one of those quite simple models that we can still learn a lot from. In vacuum, the Coulomb potential looks like this. So we have, and between two positive charges, this is repulsive, and it has a dielectric. Well, the relative dielectric constant in vacuum is always one and independent of temperature. Whereas in water, the scenario is different because now the relative dielectric constant epsilon r contains all the rotational and translational degrees of the solvent, so it actually is temperature dependent. And this turns the interaction to actually be a free energy rather than a potential energy. And we get the temperature dependence of the dielectric constant. And if we then split up the free energy into the enthalpic and the entropic component through this temperature derivative, we see actually that the sign of the enthalpy takes the opposite sign as the free energy. So if the free energy is positive, the enthalpy is negative. And this is a result of the unique properties of water and some other solvents that at room temperature, the temperature response of the dielectric constant via this derivative is less than -1. So it's not true for all solvents, but it's true for water and some other solvents as well. So this could explain part of the overall stabilization of the fixation of the second potassium ion, but still the contribution was quite small. So we decided to go more into detail and perform molecular dynamic simulations of the receptor, which had not been considered yet. So what we did was principal component analysis on the pairwise distances within this receptor, which revealed a free energy landscape and 4 distinct conformations, which is located in this space in these darker regions, blue and green. And we found one collapsed conformation where both crown edges was bent in towards the cavity, one conformation which was extended where we were bent out, and then 2 skewed conformations bending either to the site that first binds in the potassium ion or in the other way. Yes, and we also looked at the probabilities of these conformations, and we saw primarily that the probability of the conformation of the collapsed conformation increased both as the first and the second potassium ion bound. And through an energetic analysis, we also found that the internal energies within these complexes alone are responsible for a large contribution to the overall enthalpic stabilization. We performed these isothermal titration calorimetry experiments for different salts, and whereas the results for potassium chloride and potassium iodide gave similar enthalpic stabilization, we found a significant amplification of the stabilization for potassium thiocyanate. And this indicates that the counterion also has an important role to play here. So something special is happening when we combine the potassium ion with the thiocyanate. And this motivated us to use also the force field that we developed for thiocyanate, and we combined it in this study. And we specifically looked at the local bulk partitioning coefficients as a function of the distance to the receptor. So it tells us how much do these ions want to be close to the surface, basically. And we saw that the thiocyanate ion, as evident from these peaks in yellow, gray, and blue, preferred the surface of the receptor much more than chloride and iodide. So we hypothesized that this could be an explanation for the more negative result, although we could not perform more detailed analysis. We don't know where it sits on the molecule, for instance. We just know that it's somewhere close to the surface. And finally, we looked at, we wanted to develop a platform of methods that could efficiently calculate solvation-free energies of ions with the potential to be useful in studies of binding-free energies at a later point. So just like you translate molecules in Monte Carlo simulation, you can also displace the charge using the Metropolis-Hastings criteria. And we combine this with a method called Wang-Landau algorithm, where you sample along this charge coordinate, and every time you visit a certain point along the charge, you build up this histogram and also the density of states. So you add a biasing energy to that point. The next time you visit that point, it'll be biased and less probable to be accepted. And in that way, you actually build up the density of states along that coordinate. If you take the logarithm of that and invert it, you get the free energy, which is depicted to the right here for charging an atom from 0 to +1. And to make this even more efficient, hopefully, we also plan to combine this with another method that has been proposed before, which is the preferential sampling near solutes, where, well, in uniform sampling, you select all molecules for trial moves equally likely. But here you preferentially select molecules close to the solute with the goal to alter the environment very close to the solute more often than far away, because that will ideally be more efficient. And we tried 2 different strategies for displacing the charge in order to test if we could find the optimal way to displace the charge. So one linear move and one quadratic move of the charge. And this is still an ongoing project, and we still need to do more simulations to unravel which is the most efficient way to displace the charge. But it's an ongoing work. So thank you for listening, and thanks to my supervisor Mikael, my co-supervisors Björn and Jan, additional collaborators and colleagues Lunar for computational resources, and the Swedish Research Council for funding.
So we thank Vidar, we already thanked Vidar for the presentation. And with this, we say we take a very short 5-minute break, but we don't want to overextend. So please be back in 5 minutes, and we start, I would say, 5 minutes to 2. We continue with the questioning of and the discussion about the thesis. Okay, thank you.
All right, I'm back. Are we waiting for the chairman or? Hello, hello.
David, I can hear you. I cannot hear.
Okay, so if everyone
Okay.
can take their seats a little bit. Very good. Then we will see that this works out, but we will have the discussion between the faculty opponent and Vidar, and let's see that it works from a practical perspective. But and if we have to adjust it, we'll adjust it. But I think we will hand the word to David to start questions, and then we will hopefully this will just work. And so we will. Okay, please, David.
Thank you. Can you hear me?
Yes.
Great. All right. Again, I want to congratulate you on a very well written thesis. I really like the introduction about energy and all the background stuff. Very pedagogic and nice text boxes you made with like more detailed examples. So that's very good. Of course, you have a couple of papers in good journals, so that is also under control, so to speak. But as you are aware, this is a formal examination, so there will be questions and discussion. An exam is an opportunity to learn things for you and for me. So I'm really looking forward to the discussion. And as you also know, I had to replace Nico van der Vecht with short notice, but he had already prepared some questions, and I will use some of those. So let's start with some very general things. So you have on the cover a picture of a scale with energy and entropy, and of course this, if you put these two on a scale, that immediately raises a question to. I'm a physicist by training, so what is an obvious question you think that one could ask?
That they are, well, actually that the entropy, I mean, the energy increases with temperature, and so does the entropy, you can say. I mean, the energy is a function of the entropy. I mean, in general, I mean, if you increase the temperature in the system, you get a larger weight to the entropy, but so the energy is also increasing, so to speak.
Yeah, but since I'm a physicist, I'm of course much more simple-minded than you chemists that have lots of interpretations and things like that. So, so what I see when I see this picture is I see on the one is an apple and on the other is an orange.
Okay. So yeah, you mean that they can't be weighted against each other, or? Yeah,
they have different units, right?
True. I mean, yeah, I have to say that this front cover was not meant to be very scientific correct, but more with a pedagogical aspect to it. I want to make something, but I see what you mean, definitely.
Of course, you could bluff your way and say it's T times S, so then it's also energy. But
yes, yes, of course, yes.
Yeah, no, that's okay. But it's just it's a nice cover. So I mean, if it inspires to discussion, then it's all the better, I think.
Yes.
So, but basically, along those lines, so if physical and chemical processes are determined by changes in free energy or chemical potential, and to physicists, I guess the free energy is a fundamental thing, while chemists would like to discuss rather how energy and entropy drive processes. So this is, of course, rather, it is a bit vague because it's like an interpretation of how in this case, actually, Nico thinks that physicists and chemists work. But do you agree? And if so, can you explain why physicists and chemists approach this in a different way? The free energy?
Well, yes, I'll try. So physicists generally, I would say that they approach the problem from maybe a more atomistic perspective, where you have, well, specifically in statistical mechanics, you evaluate probability distributions of different microstates, and some of these states are more probable than others. And well, if a system goes from a set of microstates that are less probable to a set of microstates that are more probable, that will decrease the free energy. And that will maybe be the physicist's point of view of the free energy, whereas in chemistry, you generally measure, for instance, heats, as in isothermal titration calorimetry, for instance. There we get a direct measure of the enthalpy, but that's more on a microscopic scale, I would say. And yeah, maybe that you're more concerned with measurements in the lab rather than atomistic models.
But how about driving forces?
So yeah, yes. Well, from a physicist's point of view, in molecular dynamics, for instance, you can view molecules as colliding with each other and exerting forces on each other, and in that way they move about. Whereas in chemistry, yeah, I mean, you study a lot of things in chemistry, but you're more concerned with the average behavior, in a sense, I would say.
Mm-hmm.
Well, all of these collisions are happening in experiments, but you don't. Well, you can't really bother with that when you're measuring something in the lab.
Yeah, so actually the driving force is basically the thermodynamic force, right? So it's not like the mechanical force that you're referring to. And this is the kind of thing that you have been measuring in paper 3, for instance.
Yes, yeah.
So that's yeah, and chemists like to think about hydrogen bonds and van der Waals interactions and that kind of thing, interactions that you can easily comprehend. And entropy is always more vague, of course, to most people.
Mm-hmm.
But let's go a bit more specific on the same topic. So ions on the surface, and I showed some of my earlier papers, and now you've also worked on the surface tension kind of things. So we know that these weakly hydrated anions have a strong surface propensity. So what drives this adsorption? Is it enthalpy or entropy or something else?
I would say that it's enthalpy primarily.
Yeah,
well, it could actually be both, but I would say that the dominating factor is the enthalpy, I would say.
Can you be more specific?
Yes, because if you confine the atom to the surface, I mean, in general terms, you would decrease the entropy because it's confined to the surface.
Mm-hmm.
Whereas in bulk solution, it's free to move anywhere in the solution. And also, well, we have a shift in the dielectric constant, which is a measure of the decay of interactions.
But that's a bulk property, right? The dielectric constant.
Sorry?
The dielectric constant is a bulk property, right? Not surface related.
Yeah, that's true. But if you're considering the air, it has a much lower dielectric constant and more weakly hydrated properties would in comparison prefer that less polarized or polarizable phase. I mean,
but if you turn it around, so you're talking about, and your papers are about weakly hydrated ions. Mm-hmm. So turn around your perspective.
Okay, so yes, so they don't like the water as much as more strongly. So the thiocyanate ion, for instance, does not like to interact with the water molecules as much as for instance, a fluoride ion. And the propensity for the surface is a balance between the interactions with the water molecules and some other phase, for instance, the air phase.
Yeah, I think, yeah, so now I think you're on the right track. So I would, people often try to talk around the water, but of course you're talking about hydration, so that's very important. So I think the thiocyanate ions actually love the water, but the love is not mutual, so to speak, and water prefers itself. So the water-water interactions are stronger than water-ion interactions. And
Right.
yeah,
Yes, I agree. Yes.
and this is a very subtle balance. So as I think you already mentioned, fluoride is not on the surface because it's entropy and enthalpy together. Yeah. Okay, good. Yeah, so you write in your thesis a couple of quite high level, or you try to explain things in like a nice way also for the casual reader, I guess. So you have your explanation of the sled going down a hill and things.
Yes.
And you also write about lighting a candle. Now, I didn't notice, I forget where I wrote this chapter 2, but
I think it's just in the
yeah,
beginning.
exactly.
Yeah.
Right. You say when you light a candle, chemical energy stored in the bonds of molecule is released as heat.
Yes.
So, but why do you light a candle in general?
To get light in general.
Exactly.
Yeah.
And so most of the energy, do you know how much of the energy goes to light and how much goes to heat?
Oof, no, I don't know that. I don't know that balance.
No, so I didn't know either, so I Googled it, of course. So it's 75%. So that's
Okay,
actually
goes to light.
Yeah.
Okay.
Is that a lot?
I would say so, yes.
If
It
you
sounds
compare
like
it to a car running on gasoline?
Definitely.
Yeah. So do you know what the car efficiency of a car is, a gasoline car?
Approximately 35, 40% or?
Yeah, it's in a good case, I think.
Yeah.
So and you write about these things as irreversible conversion of energy. So can you give a biological example of irreversible conversion of energy?
Well, the digestion of food is one example, I would say, because when we then chemical energy stored in the bonds of whatever we eat or released to maintain a lot of function, but also as heat, which
Exactly.
is irreversible. Yeah.
And this can easily be tested by running around the block because you'll get warm.
Yes.
Yeah. And do you know what is the efficiency of our body in converting that energy into, so converting food into motion, for instance?
I won't remember that it's higher that typically, or I'm just thinking of this food chain when you need more biomass, and 90% is something like, but I don't know if it's correct.
No, I think it's similar to a car, actually.
Okay.
Yeah. But this is of course difficult to measure. But so if you when I was a PhD student, I went to the library once, and we had an old-fashioned library. So I picked out the 1867 volume of the Journal of Chemistry, and there you had those papers by the people like Helmholtz and Gibbs, and they worked on this. And they said, we put 4 prisoners on a treadmill, and we measured their energy consumption. So there are old measurements of these things. Before ethical permits came into play. Okay, but let's go back to a bit more nitty-gritties. So you, in your presentation and also in the thesis, for instance, in equation 4.5, you write the electrostatic interaction, including an epsilon r. Now, I realized that you use that in paper 3, but if you do atomistic simulations, why is there an epsilon r?
There is not actually. If you remove the solvent explicit, if you don't have an explicit solvent, you have to set an epsilon r. But in the case with explicit water molecules, it disappears because it's already taken care of explicitly.
Exactly. Yeah. Okay. We'll come back to that in a bit more detail a bit later. But and then in your chapter 5 on molecular simulation, you mentioned the different kind of models, and you also showed that in your presentation today. So in your presentation, actually, you added a remark, but I would just like to discuss it slightly more. So even though you haven't used coarse-grained models yourself in the thesis, you write very nicely that we can, with coarse-grained models, we can reduce the computational complexity and allow for longer simulation time. So my question that I prepared was, why isn't everyone using coarse-grained models?
Well, because you lose some detail. I mean, if you want to study a large molecule like a protein, you can represent a whole series of atoms as a single bead, for instance. But it's quite, well, it can be quite difficult to parameterize these large entities because you have to capture also the atomistic behavior within this small set of parameters in general.
Yeah, it's basically like you wrote in also in the presentation. Do you put all one minus sign for all the ions, whatever the chemical composition? So you lose those kind of details, and to a point that one has to wonder what is left. So that depends, of course, on how far you go with the coarse graining.
Yeah.
Let's see. Right. So then I think you find a nice balance in the thesis between like providing some detail for the reader, but not too much. So you explain some of the potentials and the periodic boundary conditions and these kind of things, which are important concepts. And then you also explain the integration algorithm.
Yes.
And you say that the leapfrog algorithm is identical to velocity Fourier, which is correct for the microcanonical ensemble. However, it has some practical drawbacks in the canonical ensemble. For instance, when you use the Nosse-Hoover thermostat. Are you aware of these things?
Oh, I'm not sure if it's related to that, but the one thing that comes to mind is that it's not possible to calculate the kinetic energy and the potential energy simultaneously.
Exactly, yeah. So that means that if you want to scale the velocities, you have to interpolate somehow the kinetic energy.
Right.
Yeah, and this gives a small but systematic error. So this is why, for instance, the GROMACS developers have moved away from the leapfrog. Yeah, and then it's quite interesting. So I don't know whether did you write the whole thesis sequentially from start to finish, and then because I'm looking at figure 5.3, so you do a like simple comparison between Monte Carlo and MD.
Yes, yeah.
But then later on, actually, you make it a bit more. You say that, okay, the move that I just advocated as what is so great about MC actually is never going to happen, right?
With MD, you mean it's never going to happen? Yeah.
With MC, because it's, well, you write a bit later, in a condensed phase, you could never do like a step from 0 to 1.
Yes, yeah. I mean, if you have a very crowded system, it could be a problem in Monte Carlo because wherever you try to place the molecule, you have overlap.
Yeah, exactly.
So that could be a problem if you have a very crowded system. On the other hand, if you have more separated free energy barriers, but large, it's often it can be more efficient with Monte Carlo because of this thing that I tried illustrated in figure 5.3.
Yeah, exactly. So, I mean, it definitely has some advantages. It also has disadvantages. So I guess the application should decide what you should use. But it's good. I mean, you can use Monte Carlo in a very abstract spaces, for instance.
Right.
So it has definitely has its place. So I also like that you explain things like detailed balance and things, because these are things that actually are very important, but most people, at least in the biophysical community where I'm was brought up in, like not to take too much notice of these things and hope that someone else has implemented that correctly.
Yeah.
So I appreciate that people actually like that you take the time to explain it and comprehend it yourself.
I enjoy those things as well. I think it's quite fun with the fundamentals to try at least. Sometimes it's very difficult, but it gives a lot back.
Yeah, and I agree. Also, like your images, because they are. If you have a nice image, it's so much easier to convey a message.
Definitely.
Yeah, so that's really really good stuff.
Thanks.
Okay, I skip a couple chapters and go to chapter 9. So let's talk again about weakly hydrated ions. So can you once more say what you mean with a weakly hydrated ion?
Yes. So yes, weakly hydrated ion would the interactions between the ion and the water molecules is less favorable than between the water molecules. You can say so that means that the water molecules rather want to be with themselves rather than the ion, and generally can push the ion to the air water interface, for instance.
Yeah. And so would you say so some people have for instance talked about iodide as being a hydrophobic ion. Maybe that's a bit exaggerating, but is there like a correlation with the free energy of hydration?
Yes, I would say so. I mean, the larger the free energy of hydration, I would say that you in general you have a weaker hydration in that way. Yes.
Yeah, exactly. So I mean, the fluoride has the strongest, the lowest.
Yes, the lowest.
Delta G. Yeah.
Yes.
You should be careful with large and small, of course. Yeah. And then, as a physicist, that I'm just using that as an excuse to basically attack chemists. But let's go back to the Hofmeister series. So it's very famous. It's very old. So what does it actually measure?
So originally it is measuring originally it was formulated as how much the ion salted out proteins. That was what was measured. And so some ions increase the structure of proteins. Well, yes.
Stabilize
them. Yes.
Yeah. But now, so this is of course something. Yeah, this is well known, and of course you can reproduce it in the lab. Do you think it works the same for all proteins?
No, I don't think it does. Because I don't know exactly on what proteins this is actually valid for. I guess on quite a lot since it's well accepted in theory, but I'm sure there are proteins that have specific sites that make them I don't know, more soluble in pure water and probably interact favorable with some ions that is opposes the Hofmeister series, I'm sure.
Yeah, and how about the mechanism? So do all the ions salt out proteins or stabilize them in the same mechanism?
No. I would say that some ions bind to the protein and make the hydrophobic parts more soluble, and thereby actually sort of, well, destroying their tertiary structure, I think it is. I mean, their overall structure. They since these, because the hydrophobic parts are generally hidden inside the protein, but if the ions bind to these parts, these regions are able to be more exposed to the solvent. So that's one mechanism. I think they can of course also bind to the polar regions of the more polar regions of the proteins, and that would also lead to more stabilized protein, because you have charges on the surface of the polar parts, I would say.
Yeah, I think you're right in the thesis that thiocyanate binds to amide bonds, so to the backbone.
Yes.
So that is yet another
It
mechanism.
also depends on the protein, but in general, I would say, yeah.
So basically, we have a very famous series, but it doesn't work for all proteins, and all ions work on a different way. So we are really comparing apples and oranges, I think. And
yes.
And so it's of course, it has its historical place, but I don't think it's much beyond that. But that's fine. So let's move on to some of the papers, and I started paper 1. So you calculated the charges on thiocyanate with DFT, including a hydration shell, and you observed charge transfer to the solvent. And in other words, the ion does not have the full -1 charge. And actually, if I look at, let's see, I've written it down, figure 1, it looks like 0.3 electrons are transferred to the water molecules. Is that correct? Something like that.
Yes, I believe you're correct. Yes.
That sounds like a really a lot.
Yes, I agree.
Can you explain?
I mean, the nitrogen is quite electronegative and quite small. So I guess it's primarily due to the polarization from the nitrogen atom on water molecules. Well, I'm actually not sure.
Yeah, so one thing that I have a question about there. So there is, you use a method that is called low prop. I'm not familiar with that method. So there are there's a ton of methods, of course, to derive charges from DFT or quantum chemistry.
Yes. I mean, personally, I did not perform these calculations. I'm not sure about the very details, but I know that we performed these calculations with both MO6 and DFT level of theory. And actually, it's a little bit confusing here, because we report results for MO6 here in this plot. But these methods produce very similar results for the charges. So at least we had 2 different methods that produced very similar results, and therefore we chose to go with one of them, the MO6.
Yeah, okay, let's not dwell on this. So maybe I'll look up this method, because one, you can do a quantum calculation or DFT calculation and get very similar results, but then if you do the partitioning of charges to atoms, you can actually get very different results.
Right, right.
And this is basically an unsolved problem for which there are only approximations. But
Right, yeah.
so despite the fact that you then find that you have like 0.7 minus 0.7 electrons only on the thiocyanate, you scale it up again to -1. So why is that?
Well, in general, you want to, if you want to transfer these charges to a molecular dynamic simulations, the general rule is that you should keep it electroneutral. So if you pair this ion with positive charges that has +1, for instance, as we did in our study, you have to make sure that the anions also cancel these charges. So
yeah, that is of course a practical thing, but yeah, please go ahead. Yeah.
Otherwise, we deemed the ratio between the charges on the nitrogen and the sulfur to be an important property with implications for the properties at the air-water interface and the orientation specifically, and also at other interfaces as protein water, for instance. So we wanted to keep this information from the quantum calculations, but still fulfill this condition for the molecular dynamic simulations. So we just made that choice to keep this ratio fixed while scaling those charges and keeping the charge on carbon fixed.
Yeah, I actually checked. I have some old calculations on this ion as well, and I find similar, but in vacuum. So I find similar results as you have here in figure A. So those results are likely correct.
Okay.
And I agree actually. So the ratio between the carbon and or between the sulfur and the nitrogen is of course important for the overall properties, and it definitely influence also the surface properties that you looked at. But this is a field that is actually quite active at the moment. So I'm not sure whether you're aware of that, but there are groups that use actually scale charges on ions. So they would actually put -0.7 on this and +0.7 on the potassium.
Right. Yes, I have heard of that. Yes.
And do you know what is the rationale behind doing these kind of things?
I think it is because, as we pointed out earlier, we set the relative dielectric constant to 1 if we have all atom simulations. But in fact, I think there has been made measurements that or calculations or measurement, I'm not sure, but that proves it to be rather 2 actually, the relative dielectric constant. And I've heard that one way to compensate for the fact that you're using a value of 1 is to scale the charges instead.
Yeah, that's correct. Or let's say that you're on the right track. So yeah, so I guess you have worked with water simulations. You have used SPCE most of your work.
Yes.
But do you know what is the dipole of SPCE and how that compares to condensed phase measurements or gas phase measurements?
I think I've read it at some point, but I don't remember actually.
Yeah, so so in gas phase, the dipole is 1.85 for water, and in ice there are measurements where it's about 2.9. And those water models, they are like 2.3. And this is, this is typically called effective pair potentials. Do you know why it's called effective?
Well, first of all, they're assuming pairwise additivity, one thing.
Yes.
And yeah, I mean, there are also some. I mean, the Lennard-Jones is one way to model a potential, but it's that captures the general behavior, but it's not really.
We should please try to talk about or think about the Coulomb rather than
Right.
the Lennard-Jones.
Effective, yeah. The pairwise additivity is one thing that makes it effective, so that you're neglecting many body effects, for instance.
Yeah, exactly. So now you're exactly on the right track, because that's what the SPCE model is about. So it adds a polarization energy basically to the typical or the previous models. But all the water models, they have a charge that is or dipole which is larger than the gas phase dipole.
Right. I understand. Yeah.
And
To
this
take into
is
account the polarizability, which is not included in the potentials.
yeah, exactly.
Yeah.
But then there's if you would have explicit polarizability, which of course you are aware there are quite a few models. One of the oldest is actually from Lund, from Peter Ahlström and co-workers. So these models instantaneously respond to an electric field. And if you measure the dielectric response in like most organic materials or light non-metals basically, then you would see that that this dielectric constant of this polarization response is roughly 2. So actually the dielectric constant is frequency dependent. So at what you have been measuring further on in the thesis is the epsilon 0 at 0 frequency. What is typically called the dielectric constant, but there's a frequency dependence, and the infinite frequency is the instantaneous electronic response, and this has a dielectric constant of roughly 2. So there are also models, this is called the electric continuum model, that do not scale the charges of the ions, but they just run the whole simulation with a dielectric constant of 2.
Okay, yeah.
But then you have to reparameterize the water as well, of course. So,
right.
Yeah. Okay, this is messy business. Let's see, let's move on to surface tension. So in figure 13 in this paper, you show 2 methods to get information about the excess surface tension. And which one? So one is based on the Gibbs absorption equation and other on the pressure tensor, basically. So which is more computationally efficient?
The pressure tensor, because that you get often directly, I would say, on the fly.
But does it converge rapidly, or do you need long simulations?
I would guess that you would need long simulations, yes.
Yeah, I agree.
Because you're comparing sort of very small changes compared to the overall pressure between different ions. So.
Yeah, exactly. Especially if you want to do a series like you did, then
yes,
to get reasonably converged results, you need long simulations and large systems. But in figure A, then you see the surface excess for the chloride salts. So that's the red one, and it's nonlinear. You think that is? It looks nonlinear, but is that valid in view of your error bars?
No, I wouldn't say so. Actually, it might as well be linear. I would say.
So is it really different from the thiocyanate salts? I mean, it's the different numbers, of course, but
yeah, no, I agree. I mean, the errors are very large, and it's hard to conclude actually, like if they are statistically different.
But But the sodium iodide seems a little bit more clear.
Yes,
it-
that seems like some tendency, which is
Yeah.
not linear at least.
Are there experimental data for these numbers for the surface excess? I guess surface tension, of course,
No.
but
No, these are only fitted to the equation. So in this paper, we didn't find any experimental data on these.
no,
Only
I
for
think
the excess.
this is very hard. You have these surface sensitive spectroscopy techniques, of course, but photoelectron spectroscopy. But I don't know whether you could get this in a reliable way, but maybe you can.
Right.
All right, let's move on to paper 2.
Mhm.
Let me just open it. Yes. So yeah, so I showed one figure from that paper and the figure 3.
Yes.
So the ripples at the cutoff.
Right.
So can you explain where they come from?
The ripples at the cutoff. Well, the cutoff is the place where the interaction is electrostatic interaction is approaching 0, and that behavior close to this value is dependent on how many moments you cancel. So there can either be, there can be, for example, if we look at the figure on the page before, figure 2, for one moment cancel, we even get a linear curve, which is not with derivative of. It's not possible to take the derivative, and that's dangerous because then you can get impulsive forces, for instance.
Yeah, I think that is very comparable to what I used as a switch function as well, and it has a similar effect as well. So there you have a non-monotonous derivative.
Yes.
But are the forces completely smooth in the higher moments if you go from 2 or 3 onwards?
The cancellation is p-1 of derivatives of the potential. So if you put p equals 2, you cancel the force, and then you cancel the derivative of the force with p equals 3.
But with p equals 2, there are still ripples, right? Or no, hang on. Okay, you have too many curves in one plot, or maybe I should just make it bigger. I'm looking it on my screen, but you have also the SP1 and SP2, which are SP3, which make it a bit more hard to read.
Yes, I think there might still be some ripples for those higher orders as well. The higher orders, I don't know, maybe higher orders of the force could also, if you don't cancel them, that could also lead to instability in some way, because in general, you take into account the interaction, or you cancel the higher order moments. So canceling the force is equivalent to canceling a dipolar artifact. Whereas if you go higher, it's the quadrupole artifact at the cutoff. So I would say that, well, we haven't really looked into detail about this actually, but I would say that higher orders could potentially also have effects at the boundary where it goes to 0. Potentially, I would guess that. I'm not sure about the detailed explanation for it.
So traditionally with cutoffs, what one considers is that you have 2 molecules which are oriented when they are close. They move out of the cutoff, they become unordered relatively, and when they move back into the cutoff, they suddenly feel a force again. Now, by switching it slowly off like you do, this force will be very small initially, but when
Right.
they come closer, the force becomes larger gradually. So there's still maybe some effect of that.
Right. Yes, I believe so.
So it would definitely be good to test this on like more complex systems. Let's see. Okay, let's move on to paper 3. Hang on. Right. So in this paper, you use this isothermal titration calorimetry, and you use it to determine those two binding constants and two corresponding binding enthalpies. And that is a very interesting result indeed, that the second one would have a lower enthalpy than the other one. But can you explain the binding models? I couldn't find really any math in the main paper about describing those models. Maybe that is trivial stuff for the experts, but I'm not. Yeah.
So we evaluate two different models, and to start with the major difference between them, the single set of independent binding sites model assumes that the binding sites are independent. So you just fit one binding constant, which is valid for both binding sites. And the other one assumes interaction between the binding sites. So you fit one of each, one set of parameters for each site.
Right.
And the second binding event is defined as the first one is already bound. So it's the dependence on the first bound potassium ion.
Right. Okay. And now I see it. Figure 2B and C.
Yes. Exactly. Yes.
Oh, right. And then you distinguish basically by saying that the chi-square of the fit is much better if you have sequential binding.
Right. Exactly. Yes.
Right. Okay. Good. Now I'm with you. So that was actually. And also your error bars seem reasonably small. It becomes a bit bigger for the first one. So if you just have one binding event, of course you have. So you fit either one or two numbers, basically, right?
Yes, exactly. Yeah.
And no, actually, is it just one number or?
No, it's 2 or 4 numbers. So it's
exactly.
1 or 2 number for each site. So
right.
So the equilibrium constants you fit to determine the concentrations of each species. You get the concentration balances from your measurements.
Yeah.
And then you fit it to the heats as well with the enthalpies. You can say.
Yeah. So, but then I'm just looking at the error bars. So you go from 0.02 kcal per mole with the single binding constant to 0.07 and 0.31.
Yes.
Does that tell us anything about like the accuracy? Well, of course it does, but about which, does that invalidate your choice for having a two-state model, or invalidate is maybe too much?
You mean? I mean, the fact that the errors are larger for the sequential binding sites model. I mean, in general, I would almost say that the more parameters you have, the less errors you get because of fitting on more parameters. But here it's almost the opposite. But I'm not sure. I mean, I think what we evaluated was basically the sum of deviations from this fitted curve. And
Yeah, I
I'm not
guess
sure,
it's
I'm not sure if I have an explanation for the larger errors in the first one.
I think actually it makes sense to have larger errors, but it depends a bit on how you calculate how the errors were calculated.
Okay, so we did 3 replicas, and then we fitted.
Oh, that was okay. Yeah, that's true.
Yes, we fitted with all 3 sets of points, and then we got the standard deviation among these 3 measurements.
Right. There's another actually very powerful methods to also estimate uncertainties, and that's bootstrapping.
Right. Yes. And actually, I started out with using that when we only had 1 set of. No, sorry, that was for the simulation part. I did that for the Van 't Hoff plots.
Mm-hmm.
For the then we used bootstrapping for the simulation results.
Okay. Yeah.
But I know I could probably use that for these plots as well.
Yeah, I think you have enough points, and the curves are smooth, so it should work. Yeah, so you get another lower limit for the errors anyway. So
yes, yeah.
It may turn out actually that the single binding constant experiment is maybe a bit too optimistic. If you would do a bootstrap analysis, you would maybe get a
yeah.
But it's good enough. I think. I mean, it's still quite. Yeah, it's quite strong evidence for the sequential binding mode anyway.
Okay, yeah, I would.
All right. So in this paper, you have in table 2. I looked a bit at try to comprehend those numbers. So if you just look at the difference between KCL and KI, just experimental. So the differences are very small, right?
Yes.
So maybe it's because I have been working too much with like simulations and these kind of free energy calculations that you also have done. But I would say the difference between so what you if you would make a thermodynamic cycle out of these measurements and you do the KCL measurements and the KI measurements, and then the difference between them is basically the hydration free energy of the anion, right? Or what am I missing? It's maybe a trick question, but
Well, no. If the ion is not interacting at all with the receptor or the complex, I would agree, because then the difference only depends on the. Well, actually, if I mean, the solvation-free energy or hydration-free energy of the anion, that would not matter if the anion didn't interact with the complex, I would say, because those terms cancel when you calculate the free energy.
yeah, but let's say you have your complex in your simulation now, then so that you can really control and you can do funky stuff. So you have your KCL complex, and then you change a chloride ion in your box to an iodide ion using a free energy protocol. Would you see any difference? So that's basically so you have the 2 legs in the thermodynamic cycle, which is basically the binding. And then the other leg, I'm proposing a 3rd leg, which is then going from chloride to iodide, which you can do in the simulation, of course. If you do it in pure solvent, the difference is 15 kcal per mole.
Right.
So why aren't you seeing 15 kcal per mole here?
Well, I would argue that term, most of that term cancels because, well, the way I've constructed the cycle is that I first grow in the ion pair in pure water, and then grow it in where the potassium is bound to the complex, and for instance, the iodide ion is grown into solution. So well, those terms, the solvation or the hydration-free energies induce those two systems from hydrating the iodide. Most of that cancel, I would say.
Yeah.
Most of that cancels, and the rest is only due to interactions if the counter ion affect the complex in some way.
Yeah, I think that's correct. So, yeah, but it was a bit confusing for me to read. But I mean, these are rather complex systems with
They are, yes.
4 different compounds, which is more than just
Definitely.
water, then it's a lot. For me anyway. Let's see. Yeah, so you look at those internal energies in figure 5. So you basically calculate the energy difference between having 1 and 2 ions bound, or 0, 1, and
Right.
2.
Yes.
But you're not taking the water into account. So aren't you missing something?
Definitely. There is, I mean, this is only considering the interactions within the complex, which of course is generally a large contribution, but we wanted to isolate the contribution from only the interactions within the complexes. So what we did was that we reran the trajectories, but only in GROMACS, and calculating only the interactions within the complex.
Yeah.
So it is according to structures, of course, with the water, of course, but only the internal energies.
And in this internal energy, the repulsion between the potassium ions is included, I guess?
Yes.
Yeah. So you find that these numbers are basically indistinguishable, right, in table 4.
Yes.
Yeah, so that makes, well, actually it's not obvious actually, but the interaction with the crown ether is so strong that it's that the repulsion is basically negligible.
Yeah, there is a small difference, but it's small compared to the overall.
Yeah.
Yeah.
All right, then let's move on to yeah, the counterintuitive finding. So and this is with some help from Nico van der Vecht, who also was a bit confused about this. So you say that the enthalpic potassium attraction is small but important contribution to the overall interaction. So let's start by just answering you more or less open questions. So so what do you mean by saying that the enthalpic attraction contributes to the overall interaction?
Well, it always contributes to an interaction, but if it's negative, it's a stabilizing component to the free energy. Or I mean, a favorable component to the free energy, I would say.
Right. So yeah, go ahead.
Yeah, no, sorry, that was basically.
Yeah. So and is it correct that basically this analysis is based on the continuum electrostatics?
It is, yes, because we're considering the solvent as a continuum dielectric.
Yeah.
But what is the main point is that the temperature response of the dielectric constant is measured experimentally.
Yeah, that I understand.
Yeah.
That's fine, of course.
Yeah. But yes, it is.
But if you look at equation 1, then, which is in the paper, which is what you write down for the cation interaction, right? And you also presented that.
Yes.
So this is the Gibbs energy, or the continuum estimate of it. And then you do the math and calculate the enthalpy. And then if you compare that to page 157, sorry, the entropic contribution.
Yes,
So this is in the supporting.
Yes, in equations S3.
S3, yeah.
Yeah.
So if you add these two up, H and T delta S, you see that Gibbs energy effect of this is totally 0. So they exactly cancel each other.
Yes, right. Yeah. Yes. Well, I'm not sure I understand your question, or you mean that the entropic part and enthalpic, they cancel each other to make a free energy close to 0, or?
Well, according to your equations, that's what they do, right? Or am I missing something?
Well, we don't know the free energy, actually. We don't know, well, the free energy of interaction depends on it's not included in these equations. It's only the relation between the free energy of interaction to the enthalpy and the entropy. So depending on how large magnitude you have of the free energy, you will also get a large magnitude of the enthalpy and entropy.
But you write an equation for this free energy, right? That's the equation 1 in the paper. You just postulate that the continuum electrostatic model for the charge-charge interaction.
Yes, yeah. In this case, it is small. In this case, in this particular case, with two monovalent ions at that separation in the receptor, it is small.
Yeah, but okay, I'm not so much interested in the numbers, because I mean, of course, that can depend on these kind of things. But basically, with this definition, yes, if you do the temperature derivative, you get an enthalpy and you get an entropy. But if you add them up again, they cancel. So this that means that this cation interaction does not contribute to the binding free energy.
Well, yes, I would say that it does. I don't think it cancels totally. It has a small contribution. I mean, you're saying that if you combine S3 with equation 2,
so H minus TS.
Yeah, then you get G back, but it doesn't say anything about how small or big it is. Because if you combine and you get G plus the derivative times G minus G times that derivative. So you recover G.
Right.
So it only says something about the dependence on this temperature derivative.
Right. Okay. Yeah. Okay. You're right. So but basically, then we have the equation G equals G.
Yeah. Exactly. Yeah. That's what we recover. Yeah.
Okay.
Or H minus TS equals G. We get, but yeah. Doesn't matter. Sorry.
But so your paper is about, or the title of the paper is the counterintuitive electrostatics, but you could have made it even more counterintuitive. So what would happen if in equation 1 you would put a potassium and a chloride?
Right. Right, then you will get a positive enthalpy instead of bringing them closer.
Yes.
And that's also counterintuitive.
So the question is really, okay, this is like an aspect of the whole binding. So really, what
Yes,
do we learn?
Exactly. So I've thought about this, or I've read some about this, and I've found one explanation for if we have two charges of different sign, as you said, with a chloride or a potassium, for instance. If we bring them together, that's entropically that's favorable according to this model, right? Entropically, the entropy is increasing when we bring them closer. And one explanation for that is that you liberate water molecules, and that liberation from the solvation shell is included in the dielectric constant derivative as measured with this. But I've also tried to discuss with a colleague what's the reason for a negative enthalpy and a negative enthalpy and a negative entropy for the charges of the same sign, but I haven't found. I think it's still rather unknown, as far as I'm concerned, at least.
Okay, but I'm about to round off, but I have one more topic, basically, or not. It's actually the same topic. So, but so I would rather like to dig a little bit deeper here. And if you think about this continuum electrostatics, it describes a solvent as a homogeneous medium. But what does a water molecule actually look like?
They have three atoms and a dipole moment.
Exactly. So if you go back to write take an ion pair in water, potassium chloride, and if you would, we can do these potential of mean force calculations with our softwares. So if you would actually calculate the distance dependence of the Gibbs energy as a, would it look like equation 1?
No, it would not, because it also has oscillations on the way.
Exactly.
Because of the localized structure of the water around.
Yeah, so exactly. And you have the same problem when you use these at least these simple continuum electrostatics, for instance, for surface properties. If you ignore like the water dipole at the water surface, then it's very difficult to explain, for instance, the surface propensity of these ions and things like that.
Right. Yeah.
And this has been a big struggle. I mean, when we published those papers on ions on surfaces, the literature was full of people hitting each other on the head with like plus minus 20 KT surface affinity and things like that. And it's not so simple. Yeah, thank you for an interesting discussion.
Thank you.
It was enlightening and very good work overall. So with that, I would like to pass on to the committee or to the chairman.
Well, thank you again, David, for the good discussion. And okay, so we end this faculty opponent questioning, and then we can turn to the committee questions.
Right.
I think maybe we stay online and have our external visitors first. So maybe we can turn and see if Karina is with us.
I certainly am. Do you hear me okay?
Yes.
Yes, we hear you.
Good. And hello, Vidar. I'm sorry
Hello.
I could not be there in live
No.
today. I had been looking forward to meet you and discuss with you in person, but anyway, here we are.
Yeah. No worries.
And I want to thank you for inviting me on your examination board. It has been some years since I collaborated intensely with colleagues doing theoretical and force field modeling. So it was actually really great to see advances that has been done since working with ions and the orientation and distribution in liquid media. And as David also mentioned, the introduction to your thesis was very nice. And I must admit that I in particular enjoyed your explanations on the spontaneous processes and entropy. That was nicely conveyed.
Thanks.
Before I move on to questions, I think it might be relevant for the audience to know that I'm a geologist, I'm also a chemist, and I try to be a molecular geobiologist also. So some of what your topic here is way above my head, but I certainly see some relevance, and I guess that's also why I'm here today. So I'm thinking a lot about interfaces between minerals and molecules in liquid media, and how ions in the media affect this interaction, as well as structure the liquid surrounding an absorbed molecule. And even though your work can seem very specific and narrow, it has great implications for my field, I think, and also for many other scientific questions. And already in your introduction, you highlight a very important one. You're kind of stating that studying chemical systems on the atomistic level enable us to obtain insight into why materials or molecules and solutions behave the way they do. And I think that's a very important point, and I agree with that very much. There has been a tendency recently, especially with the advances of vacuum-based microscopy, that people like to infer processes or mechanisms from a still image taken out from a reaction. So I would like to congratulate you to bringing more attention to this field and also contributing to this topic.
Thank you. Thank you.
And also, I want to say that your thesis was it was a nice read and it was well structured. So also congratulate on that. And I also did enjoy your presentation. And you actually managed to address many of the questions I had. David took over mostly many of the remaining ones. So what I mostly have left is sort of on the reflective side and applications to a broader picture. And you did touch upon it already, but I really liked your figure S10 from your thesis. So the SGN ion clusters. And yeah, the snapshots of the SGN ion clusters. And in your introduction today, you mentioned that nitrogen in the SGN molecule interact more with sodium than with sulfur, and that potassium more with sulfur than with sodium or with nitrogen. Can you elaborate a bit on why that is?
Yes. So we argue that the smaller, more electropositive sodium ion is more prone to interact with the smaller, more with a higher density of electrons of the nitrogen, since they are more similar in size and polarizability, I would say, whereas the sulfur and the potassium are larger and have similar properties, are more similar for those ions.
So when you saw these snapshots, what was most puzzling to you or surprising, or did you expect to see this picture you obtained?
Well, I don't think, well, maybe the part where the potassium is more attracted to the sulfur was not very surprising in regard to their size in the models. But the fact that the sodium and the thiocyanate interacted on a longer range, apparently, and with the implication that they formed larger clusters, that was surprising for me. Mm-hmm. And also that it's much more localized at the edges of the. It looks like it's at the edges of the nitrogen atom, and I don't have a detailed explanation of why that is, but the applications of it was unexpected.
Mm-hmm. Yeah, and I agree. I also was surprised by the longer range with the sodium. Mm-hmm. So for me, clustering of ions and ion molecule associations draw relevance to kind of what I'm working on these days, which is preservation of proteins and DNA in sediments. So in the liquid medium, DNA degrades within 2 weeks, but in sediment, it can be preserved for geological relevant timescales.
Right. Okay.
So in my mind, the reason for that is that the DNA and the mineral kind of interact together and the immobilization of the DNA on the surface. But would you think the preservation would also be related to the ions in the media and the hydration of the adsorbed molecule?
Yes, I agree. I mean, if you have ions, I mean, well, for instance, rust is greatly, and the formation of rust is greatly enhanced if you add ions to the water around a metal, for instance. So the ions generally have a corroding effect, I would say, on well, preservation. I'm not sure how it works really with microscopic matter, such as DNA or so, but on bulk matter, I would say that ions are not good. Well, strongly hydrated ions are not very good for preservation.
And let's say we have a molecule sitting on a mineral surface adsorbed there, and then you have clusters, ion clusters in your solution. Would you expect an interaction with a charged adsorbed molecule?
No, well, not if they're clustering. That indicates that there's favorable interactions between the atoms, well, between the ions. So if there's a third component or a fourth component, that would indicate that it's not so prone to bind to that. So that's true if they're clustering, and if you want to avoid, well, if you want to avoid binding of something to DNA or so, it would be more favorable with clusters of ions, I would say. Mm-hmm. If that's what you were asking.
Yes. I'm mainly just trying to hear your thoughts of this, because I'm not quite sure either. And it's something
I'm not really sure, but that's my guess at least. Yeah.
So if we kind of hang on to your figure S10 here, so let's say you threw in a charged surface in your modeling. Would you expect to change the kind of snapshots you're getting out?
From the clusters, you mean, or?
Yes, yeah.
No, I mean, I did not have an idea of how the clusters would look before, and I was actually quite surprised that the thiocyanates, I mean, that the anions alone form these large clusters, because, I mean, they are negatively charged, and of course the cations are also sitting in this cluster somewhere. But I was surprised by the ability to form such large clusters. I think it's quite unique. It doesn't happen definitely not for all ions, so it's quite unique for thiocyanate and similar ions.
Mm-hmm. So if we added instead of a surface, maybe a more flexible molecule that could go in and interact with the ions as well more directly, how would you envision that could change what you see here in figure S10? Let's say we add a positively charged, highly charged molecule.
Okay. Well, it depends on the propensity of this ion to the molecule we introduce. If it's a molecule that has a higher propensity for the thiocyanate, this cluster formation will have a competing term, and it would depend on that balance between the interactions within these clusters and the molecule. And it's probably very specific to the molecule. I can't say anything in general. It would depend on the nature of the molecule and the sites on it, I would say.
Would it be a lot of work, sort of feasible for you to, now I'm just saying, throw in either a flexible molecule or a mineral surface in your system?
It would be possible, yes, for sure, yes. If they are very large, I mean, then it's of course a problem, because then you could have the possibility to coarse grain the simulations while maybe still keeping explicit ions. But it would be possible for most molecules, or if the molecules are small enough, at least.
And you also write that this is relevant for kind of the air-liquid interface. So how would you treat an air-liquid? And now I'm just curious because I don't know this. How would you treat an air-liquid interface compared to a mineral surface, for instance?
Well, yes, what you do in the simulations is that you have a simulation box, and then you have one part of the box is explicit, well, the solution that you're simulating, then these boxes are separated by a vacuum column. So you get two interfaces, actually, one at the top and one at the bottom, and then properties are taken as averages. That was how we did it, at least. Properties are taken as averages of these two interfaces, and then it's replicated in the other dimensions. I mean, parallel to the interface.
So what do you do in terms of charges for the air-liquid interface? Do you consider it as being charge neutral?
Well, yes, we do. We don't add a charge like on top of the atom, so to speak, but we let the explicit atoms take care of that. We hope that if there is a net charge, we hope that the ions take care of catch that effect.
Got it. So what I'm getting at is when I'm working with molecular dynamics simulation, etc., and we add other experimentalists to the collaboration, they always jump on. But what about pH? What do you do with pH? pH is so important for any reaction in my experimental system. So I would like to pass that question on to you, because I think every modeler I've interacted with has gotten that question so many times. So I would like to hear your version of
how we cope with pH.
Yes. So let's say you figure S10, if we decrease pH, let's say we have pH 4, would that look different?
I believe it certainly could. I mean, I've been doing the all atom simulations, so the strategy there would be to explicitly add the hydronium ions, which maybe I don't think there's, well, to my knowledge, this is not typically done. Usually the most pH studies I've heard about this is with this coarse grain model, and then you add it on top of what you're simulating as a part of the potential, I think. But in my case, I haven't really dealt with these systems, but I know it's a huge thing in biology simulations with pH calculations and titration and so on.
Definitely, and I think people are trying to find different ways of coming around that by introducing different types of ion, as you also touched upon. So for your study 3, I also want to congratulate you for succeeding in overlapping experiments and theoretical modeling. That's always nice to see done.
Thank you.
And I actually had a few questions to that chapter, but you and David answered most of them. So I was going to talk more about the partitioning coefficient and also your what is that? Your figure S10 again, actually. So the PCA diagrams, but I think you came around that quite nicely and showed that how we could infer the structures of your molecule from that.
Sorry, I didn't catch the question. Sorry.
No, that wasn't a question, but you kind of addressed that already, how you nicely showed the orientation of your molecules from those diagrams.
Right, from the PCA analysis, yes.
And I think that, to me, that was an elegant way of doing that.
Oh, yeah, okay, yeah. Yeah, it was very, I also like that it revealed a lot of information from that plot.
And I think that's actually concluding my questions. Am I allowed to pop in again later on, Chairman, if I have an extra question later on, or is this it?
Well, I think we will anyway open it at the end for general questions. So I think you have a chance to come back if you find something.
Good. So I don't want to be greedy here, but I may have a pop-up question. So thank you for now, and let's pass the relay on.
Thank you.
Then we turn to the local committee, and I think we're checking it with the microphone. So if you that are here remotely, if you have problems, give a shout that you can't hear this. But I think we're trying with the general microphone, and we'll see how it works for the local thing. So committee, please, and Maybe Tobias, you want to start?
Okay, so yeah, I also congratulate you. I really like the introduction, very pedagogical, very clear.
Thank you.
I have a background in biophysics and statistical mechanics, so I could understand some parts of your thesis. The chemistry part, I leave to you, Joachim, to ask questions about. So I have two general questions and then maybe a few more specific. So the first one is, I work in biophysics, and when you open a book on biophysics, then it always, and you talk about ions and ions in water. The first equation you get is the Poisson-Boltzmann equation.
Right.
My question is, why is that equation not here? Is it of no relevance for?
Yes, it is relevant. From my experience, the Poisson-Boltzmann is generally used when you don't consider the ions explicitly, I would say. But I've never actually myself carried out anything with Poisson-Boltzmann, so that's my view. And in simulations, when you treat them explicitly, you have to turn to the Coulomb interaction. That's my view, at least.
So when would it fail? I guess you in Poisson-Boltzmann, you say the only thing we worry about is the fact that ions have a charge. And
Right.
It's just the dielectric constant.
Right. Yeah, you would fail in reproducing the size and the softness of the ions, for instance, polarizability. So, yeah.
It's never used, or it's just that
I think it's used, but I think maybe on more coarse grains, well, on larger systems in general. Yeah.
Then I have a very difficult.
Okay.
So, you could help me with. So in the first page, in the thesis, you write that ions have different properties, which depend on their charge, size, valency, and polarizability. So could you explain what these properties are and how these properties are affected by this theory? Like in general, is there some general understanding? You could say if I have an ion with a large polarizability, it could be like that.
Right. Well, if you have a large polarizability, then there's, electrons move easily within the ion, and other molecules can influence this cloud of electrons and make it an instantaneous dipole, for instance, which can cause attractions, which is not due to the net charge of the ion, but due to the distribution of electrons within the ion. And that turns out to be very important for the propensity for the air-water interface, for instance, because then the ion can move the electrons, make more electro density of electrons higher, close to the water phase, for instance. It has that flexibility to adjust to different environments, whereas a less polarizability have more fixed charges. Yeah, if we put it that way, and that is not so favorable for air-water interface, for instance, and apolar surfaces in general. Whereas the charge is more long range, so that has consequences for the long ranged interaction, whereas the polarizability is mostly important for short ranged interactions.
And then also talk about size.
Yes. Size is also, if you consider, for instance, the crown eater, size is very important as an example, because if the ion is too big, it basically won't fit in this pocket. So, and that will generate a very high energy, and that's very unfavorable. And that's why some of these ions, partly why some of these ions is due to their size, that they fit basically perfectly in this pocket. It makes it very favorable attraction. So they for sure exclude volume, and that's important from an interaction point of view. also.
Can you then, this is of course speculating, but could you relate this Hofmann's series to these properties in some way?
Yes. I mean, this series is definitely correlated with the how strongly hydrated the ions are. So that's smaller, in general, smaller ions with a high density of electrons is solvated better with low polarizability, whereas ions to the right, such as the thiocyanate, has in general a larger degree of polarizability. In general, I would say. Yeah. Thanks. Okay. Yeah. Okay. Great.
Yes. We have one comment also on the kappa, which I have to ask. So, on page 41, you write, with numerical methods, we can sample the precision factors. Then my question is, do you actually calculate precision factors?
No, we never do that.
Why do you do that?
Because it's so large. It contains so many states that it would take forever to calculate.
It's exponentially of the system size.
Yes. Yeah.
More specific questions, but maybe one I could not really get into all the details, but one thing I noticed when you had your presentation was you said that many other ions had force fields. Available, but this particular ion did not. And then I think you used the term thermodynamic consistent force field.
Yes.
So what is a thermodynamic consistent force field?
Yeah, it's a little bit vague, I agree, but it generally, I mean, there are different thermodynamic properties, right? And what we meant with that was mostly that we could reproduce both properties at the air-water interface and properties in the bulk solution. And also that we did it for several concentrations, because that's quite common that you can reproduce experimental properties for one concentration. Then when you increase it, you deviate very much, which was the case for the previous force field, actually, when we looked at bulk properties. So, yes.
It's not it's a bit vague definition.
I think it's a bit vague definition, yeah.
Then take the two. I have many comments on that. I will not go through all. Maybe the main thing I noticed, I think you say that one question is, you said that summation of all Coulomb interaction with an error proportional to the net charge. And the obvious question was the error of what?
The error of the potential energy within this region.
Okay, so the average potential energy might fall.
Yes, exactly.
Okay.
The total. Sorry, the total, not the average, but the total. Yeah.
Okay.
Mm.
Then the question is, why would you then go? And then you have this Wolf method.
Mm.
It essentially cancel that error.
Yeah.
So why would you go beyond that? Because now you cancel the error you have, but still you're not happy with that. Why is that?
That's why. Well, they saw in this paper that the error was proportional to the net charge, but well, they also found that canceling the charge was significantly improved the results. But later it was also found that the cancellation of the dipole was also important to get better results. So it was not enough to only cancel the charge, because then we would neglect the dipole, or I mean the interaction. If the system it can still be a dipole, then you neglect that interaction between the environment and that dipole, for instance. That's also important. But as a first step, they only canceled the charge, and they saw that improved the results.
There were an error due to the dipole.
Yes.
That we didn't really know.
No, they saw these oscillations. How was it? I'm trying to remember now. They looked at systems where they increased the radius, where they took into account the interaction, and then they saw that energy fluctuated around the true value. And if I remember correctly, when they cancel the charge, this fluctuation becomes much smaller. Yes, that was the thing. They added a damping function, which is equivalent to canceling the charge. So then they could dampen these oscillations so that it converges faster to the correct result. But still, I mean, there was still an error, but it was smaller. Yeah.
Yeah, one more thing which was a bit puzzling to me was that we used this method as the sort of ground truth, I think. Compare your method, how well do we reproduce whatever this method does? But I imagine this method also has its drawbacks. You could periodic.
Yeah.
On the
Yes.
systems, why would you use that as a measure of how good your method is?
Well,
Somehow,
I agree that it also has it has been shown to also have its problems in some systems due to, for instance, periodicity and interaction between periodic cells. But it is, I mean, it is the reference, and it has been shown to be. I think it's maybe the most rigorous method to attempt to take into account all the interactions, I would say, since it's actually since it replicates the environment, so that it mimics an infinite system. And
but if you have infinite computer power at your
yeah,
hands,
yeah,
what would your reference system be then?
just an infinitely large system. Yeah. But yes, it's computationally very expensive, so that's why you need some scheme. Yeah.
So you didn't try like making a box larger and see how.
We did try with a few with different system sizes. Yes, and also these different cutoffs as well. But in general, we saw that the larger we made a system, the less sensitive it was to the parameters that we put.
You didn't get any questions on before, I think.
No.
So, see if we can.
We have one.
We have
also,
one.
yes.
Yeah.
Okay. I have okay, so I asked the stupid question, which is why on earth did you change the charge in a multi-parameter simulation? If you have the charges.
Yes.
So
Well,
what is the quantity you seek to calculate in the end using this method?
Yeah. we seek to calculate the solvation-free energies of ions in particular. So we want to, we wanted to develop a method that could do that in an efficient way by charging it on the fly in a simulation. And so
how is it done now? How would you do that?
So as we did with the crown eater study, what you do then is that you perform separate simulations and then you compute energy difference between neighboring simulations, and then slowly you increment some parameters in small steps, and then for each step you perform a separate simulation, and then you sum over these changes to get all. But here you do it on the fly, and well, that is more efficient, we hope, but it also has it could potentially have a drawback in that you need to ensure that each of these states are actually properly sampled, because each of these states corresponds to a different conformational space. So you need to sample all those conformational spaces with good enough. So yeah.
I think maybe in the next round of writing of this paper, perfectly clear.
Yeah. Right.
Yeah.
Thank you. Well, then, last but not
Thank you.
least, Joachim,
I'm
please.
smallest. Okay, so I would like to concur with all the previous speakers that your thesis is very well written. Not only a good researcher, but also a good teacher, at least a good writer. So it's joyful to read the introduction, which is not always the case when you've read many introductions of Monte Carlo simulations before.
Yes, yes.
I very much appreciated that. And then for the papers, on paper 1, I think David covered all the questions, or at least all the important questions I had. So somewhat unsurprisingly, I have some questions on paper 2. So I think it's a very nice, I find it very mathematically elegant, but I find some of the physical interpretations of the model somewhat confusing. So I have a few questions. So on page 1 of the paper, it writes, we show here that cancellation of every electrostatic moment is equivalent to taking all long-range interactions into account in a conducting medium.
Yes.
That sounds to me like E-world with tinfoil.
Yes, yes.
Then after equation 5, right, if an effective potential cancels all the electrostatic moments in the cell, then the total interaction energy would be given solely from the particles in the centered cell, i.e. equation 5.
Yeah.
Where you have not included the long-range interaction. These two statements seem orthogonal to each other.
Right.
Could you? Is there something between the lines that I'm missing?
I think, yes, I think the difference is that, I mean, if the effective potential itself
So what does equation 5 describe?
that's the
So that's equal, but only taking the central box.
right.
What's that? Do you know what that? I mean, that has been used many times, not so much today. Do you know what that is called?
I don't remember. I think
It was called the minimum image convention.
Right. Yes.
The reason it's not used anymore is because it's terrible.
Yeah.
Especially for dipolar systems, it gives pathologically bad results.
Right. Yes.
So I mean, and it sounds here that you're saying, at least if I read this correctly, sounds like you're implying that equation 5 is the effective Hamiltonian you get by canceling all the moments. And I don't
see your
think it
question.
is, because
No,
the results don't look pathological.
No, exactly. Yes.
But yeah, okay.
I'm also now when I read it, I understand the question as it is a little bit confusing. I'm trying to remember. But I agree, it's confusing, and I'm not sure how to. I think maybe what we meant that if you only. No, I'm not sure actually. I'm not sure.
No, so I think it's not super easy to interpret what canceling all the moments means physically, to me at least. And I think there's some contradictory statements in there regarding that. And some of them might be due to my misunderstanding.
Right. One thing I can add to that is that what we meant with in a conducting medium, if you cancel all the moments, that's equivalent to taking all long range interactions into account. In my view, that means that if it is perfectly conducting, then all interactions would be infinitely long ranged, and then not long range, but there would be a perfect response from the environment.
Indeed.
Yes, a perfect response.
That was my next question. So I get the feeling that you're putting an equality sign between the statements that you have perfect solvation of moments, and removing it.
Right, I see.
That means that it's not there, and
Right,
It-
yeah.
it's incorrect.
No, exactly, yeah.
And related to that, I had another question on paper 2. So you say that canceling moments, I can't find the place, that canceling moments is the same as suppressing fluctuations.
Mhm.
Is that true? Okay, can you elaborate on that if I could just find it?
In general,
It's a bad question because I can't find the right place in there. Okay, but let's
yeah.
ask the whole question. If you have a solvated volume, a cutoff volume,
Mhm.
and you cancel the moments, of the electrical moments of that volume on every time step, will that increase or decrease the fluctuations compared to if you don't cancel it?
Decrease it if you cancel the moments, I would say.
Why?
Because you mean the fluctuation in the energy now, or the
Fluctuations
any-
in the moments.
In the moments.
themselves.
I mean, if you let the system propagate with it will, well, the moment of the system will change all the time, right? If, for instance, the dipole moment, and but if you cancel it, then
Canceling the same as applying a reaction field. Or similar to it, at least that's what you're discussing now.
yeah. No, the moment will still be there. That's true. The moment in the system will still be there, but the you would sort of cancel the error oscillation on the energy.
I see. I mean, the cancellation as in making your derivative
Mhm.
continues at the cutoff is a sort of that's
Yes.
a mathematical.
Yeah.
I mean, it's because we discretize things.
Right.
But the other one is more of a physical
Right.
thing. So if you take a fluctuating dielectric
Mhm.
and then you in a vacuum, then there's
Yeah.
no reaction field, right?
No,
And what happens if you put it in a conductor?
it will polarize the surrounding.
Yeah, and what will the surrounding do? What will the reaction field be? If I have a dipole of the volume pointing in this direction,
Mhm.
what will the reaction field be?
In the opposite direction,
Yeah, and what magnitude?
the same magnitude.
So it will
Yeah.
perfectly cancel it.
Yes, yeah, true,
And
yeah.
will this solvation then increase or decrease the magnitude, the typical, the mean squared fluctuations of the dipole? of the central volume? If I take this dielectric
Mhm.
volume and have it in a vacuum, and then I put it into a medium,
Yeah.
which one of the two volumes will have the largest fluctuations in its moments?
The water system, because it's coupled to the other system. Yeah, yes.
So if you by cancel mean solvate or have a reaction field, then you will not dampen fluctuations.
Right.
Cancellation
Yes.
will increase them. If you by
Right.
cancellation means cutting off something to make it continuous at the cutoff, then I don't know the answer. But I
Right,
think,
right. Right, I agree. Yeah.
There are some contradictory statements in here on that also.
Mm.
Okay, less technical discussion in paper 3. So I very much like the coupling between continuum electrostatics and calorimetry. I'm less skeptical about continuum electrostatics.
Okay.
At least at a qualitative level. And it's rather clear that you're, I mean, why you have a positive delta H of binding ions in general, not the delta H, but that this is exothermic. It's easy to believe that
Yeah.
coordinating an ion.
Yes,
is
definitely, yeah.
a process. But then your delta G is smaller, or has smaller magnitude than delta H. So this is
Yeah.
is an entropic penalty to this.
Mm.
You discussed this very briefly in the beginning. That
Mm.
binding of ligands results in the loss of configurational entropy in general. That's, you're not saying that this is the case here, but then you don't discuss it anymore. From the results you have, can you analyze the why you have a negative delta S?
Yes. Well, in general, there is a large entropic penalty for constraining something in a smaller volume. So that's one part that
That's a negative entropy of what?
of binding the ion to the side
So of the ion itself.
of the ion itself. Yes.
Yes.
Ah, you mean delta delta? Yes,
No, I
no.
mean delta S.
Yes,
I
yes,
mean, that's
yeah.
clearly negative.
Right. But then there's also a more complex response, of course, which has to do with the solvation of the ion and how it changes. I mean, when the ion goes from being solvated to the binding site, it releases water molecules from its solvation shell as well, and that is associated typically with an entropy increase, I would say.
Yeah, I would also.
Yeah, typically at least. Yeah. So that there's of course a balance between those things also.
And it will be solved in a very different way inside the conflict.
Yes, exactly. Yes.
And what about the conformational entropy that you discussed in the beginning that you say?
Right.
Anything about that?
Mm.
I agree, it sounds plausible. That would be negative.
Yeah. I mean, from my guess or from how I see it, we see that this collapse conformation increases, right, upon binding.
Mhm.
And that indicates that there is the free energy of interaction within the complex. It's favorable for the binding sites to come closer, right, from a free energy perspective.
Mhm.
So that, well, if you just look at it, I mean, that conformation seems more constrained than the others as a first guess, I would say, because these sites are strongly correlated and they keep each other. They want to, I mean, they want to be more close than before. So I would say that they would generate. So this seems like an enthalpic stabilization also itself, and therefore I would believe that the entropy of that change is negative.
If you look in figure 4 itself, if you, I mean, if you, by only looking at this as a 4-state system, that is kind of what you do there. Would you say the entropy change is by only looking at figure 4? Look at the population densities of your states.
You mean just considering this as different states, basically, or
yeah, which is what you do by your
yes. Well, then they become equally likely in the end with 2 bound.
Yeah,
and that indicates that there's a larger entropy.
but both the delta S's there look positive, right? Because you go to the more equal population.
Yes, exactly.
So
yeah.
Looking at your principal components analysis, it seems like the configurational entropy actually increases of your complex, because it's true that you lift up one of them, which is previously very unlikely, and then it becomes more likely. Question is how would you calculate this by paper and pencil?
The figure 4 is from this principal component analysis. Yeah.
How would you calculate delta S from it?
Delta S. Oh, I mean,
Yeah, of course.
well, I mean, yes, I mean, you have the Gibbs entropy formula, for instance, but I mean, could you apply? I'm not sure if you can apply that directly to this. I mean, I'm not sure what that would tell me if I just applied
maybe not.
population.
How does it look?
Sum of P LMP minus sum P LMP.
Yeah. I mean, that would that give you first?
Then it would
estimation
increase
on the magnitude of the.
First approximation. Yeah.
Perhaps there's scaling factors in there. That
Yeah, I'm not sure if you could directly use that for anything.
probably not. But then, I mean, you're absolutely right that each one of these configurations can have different
Entropies.
floppiness and different entropies associated with them. And
Right.
that might be more important.
Right.
But when I looked at figure 4, I felt like it looks like the configuration increases.
I see. Yeah.
Quick question on paper 4, which is more of a type. What does the how does the Born energy scale with ionic radius?
Inversed quadratic. I mean, the square inversed.
No, it's 1/a, not 1/a squared.
Oh.
I believe.
Is it? Yeah, you're probably, yes, you're right. Yeah.
More a
Right.
typo, but it's an important typo
That's a typo for sure. Yes.
because we integrate 1/r squared.
Right. Yeah, you're right. I agree.
Then I think yes, with my other questions for paper 4. I talked enough. Thank you very much.
Thank you.
Okay, and then so we can thank the committee for adding many more interesting questions to the discussion. And this kind of terminates the questioning by the 4 people formally in this committee. So I think there might be some more questions, but I think we can open it up more broadly and see if there are more questions. And I see that Ola, who has had a shadow role here, has some questions. So please.
Right, thank you very much. I did not have so much time to read, but
No,
the
understand.
time I spent, I much enjoyed. So I would also like to look a bit on paper 3 because it's intriguing for the chemist, and some other parts maybe more so for the theoretical chemist. So you describe the sort of this difference as the delta H and delta G, but of course any delta H is also a delta H.
Yeah.
Because it's a state function. So which reaction does what you describe as the delta H describe?
Okay.
What is the reaction that we're looking at?
The reaction that
So if you take the difference between the two binding reactions, what reaction comes out? You could maybe draw it on the board since we haven't used the board.
Yeah. Right. So we have this, just draw a very simple picture.
Yeah.
And then, so here we have delta H1. Yeah, and delta H. Well, yeah, it's a little bit confusing. Maybe we should do like this instead. This is already present here. Yeah. This right. Delta H1. So, and then you mean we're taking the difference delta H. What reaction would that correspond to?
Because that's really what you're measuring here.
Yes.
Is this?
Yeah.
I mean, this delta H is also a delta H for a reaction, which is the reaction that you're actually studying by taking this difference, right?
I'm not sure what the reaction would be though, because I mean, we're measuring the coordinate in the first one, and then the second one when the first one is already bound. That is a second heat that we get. But I mean, this takes into account the interaction between the sites and the excess heat of binding the second one compared to the first. That would be this.
Because if you just take the difference between the two reactions, what you get will be 2 mono-loaded complexes giving 1 empty and 1 doubly loaded. So this will be the
Yeah.
reaction that is represented by the delta H.
Okay, sorry, I didn't understand the reaction. Can you repeat?
So if you draw two monoloaded complexes
And that's monoloaded means with one.
with one
Yeah,
potassium,
yeah.
yes. So if you draw those,
Yeah.
just take two of those,
And one more. Yeah.
yeah,
For instance. Yeah.
yeah, and then you draw a reaction arrow.
Yeah.
No,
No, I mean these are the reactants, or
these are the reactants,
Yeah.
yes. And the products are one doubly loaded and one empty.
aha, yeah.
So you redistribute that potassium ion between two singly loaded to one
Yeah.
doubly loaded and one empty. Yeah, so this will be the reaction that, no, one completely empty.
All right, right, yeah,
Otherwise this
yeah, true,
breaks
true,
the law of
true.
stoichiometry.
Yeah,
So this will be the reaction that is represented by your delta H. And your delta G. And so the question
yeah,
is,
yes,
so here you're redistributing charge.
yes, yes,
Yes.
yeah, I agree.
And
Yeah,
what sort of was a bit striking to me was that you did not do these measurements, as far as I understand, under constant ionic strength.
correct.
Is this something you considered?
No, we didn't. The argument is that the concentrations are rather low, in my opinion, at least. I mean, and the change in concentration is rather small compared to the total concentration that we used. The dilution term is quite small. I mean, the dilution term. Actually, the dilution term is actually included in the fitting as well.
But not, I mean, you still always, when I have done experiments where you have charged species, if you don't do those at constant ionic strength, you may end up finding strange things. Because the interaction, solvation, etc.,
Right.
will then change here during the reaction.
You're right.
Because
Yeah,
you're
I agree.
changing
Yeah.
the ionic strength because you're making a dye-positive species as you go, and you're also adding, of course, extra potassium.
Yes, I agree. Yeah, it is for sure. Yes, I agree. Yeah. So that's
And also for me, I mean, I did not really sort of understand this, what's even called the continuum electrostatic theory. But when I just look at the Coulomb interaction or repulsion between two positively charged species, how much does that turn out to be in the one to the right? How
Yeah,
much,
it's
if
not-
I just do a very simplistic Coulomb interact in water, how much is it?
if I remember correctly, it's only like 0.2 kilocalories per mole.
Yeah, I calculated it to be 0.3, but of course I didn't have an exact distance.
Yeah.
But so that's kind of small, right?
It is.
Compared to what you measure.
It is for
experimentally.
sure. Yes, for sure.
So would you say that you overall have experimentally shown that this interaction is attractive? Can you say that for sure?
I mean, we have shown that it's attractive from an enthalpy. I mean, only enthalpically, of course. The enthalpy is part. Yes. I mean, I would say that from the experiment, we see this behavior, and I mean, the experiments might also has its flaws, of course, with the ionic strength. But I think there's quite strong evidence that the enthalpy is indeed attractive here. Then we try to explain that with this continuum model, but we could only explain a small part, as you said. But it's also a different system, because then it's only, of course, two charges free in solution. There's no receptor there or anything.
No, so what I'm sort of driving at is that I do not dispute that there is an experimental though, that this is
Yeah.
that this
Yeah.
reaction here is exothermic.
Right. Yeah.
But the sort of the Coulomb contribution to that enthalpy is really small, whether it's positive or negative. Right?
Yes, I agree.
And so based on this, there could have been the same type of agreement between experiment and theory, even if you did not calculate an attractive force between the two positive ions. Or
yeah, I agree that the sole interaction between the ions themselves are of course very small, but there's also more complex behavior if you consider the overall interaction between the sites, because the ion has its interaction with the site where it's bound to, but potentially when the sites come close, it also forms interactions with the other site.
yeah,
And that behavior is more complex, of course, and that's what we try to elucidate with this more detailed analysis.
but it seems that I mean the other contributions in terms of solvation, etc., are
Yeah.
more important than the
Yeah.
electrostatic
And of the
repulsion
receptor,
or attraction.
exactly, and of the receptor itself.
Yeah.
Exactly, yes, I agree.
Yeah. Okay. Right. Thank you very much.
Thank you.
Thank you very much. Anything else? Okay,
I have a question, actually, and things I want to discuss with Vidar, if I may.
You may.
Can you open maybe Slack for me, please?
What?
Slack.
Okay, yes,
New part.
the file there. Maybe I should share my screen so this is for everyone to see.
It's a presentation.
I should share the screen for the Zoom. Yeah. We're out there. Yeah. Okay.
If you open that so kindly.
Yes.
and then it's here.
There. Yeah. My day. Yeah.
Thank you.
Yes.
Perfect. And you may sit there.
Okay.
So the easy part is over. Now comes, yeah. I know, do you see the Academy Awards? Like, you know, it was very spectacular this year. But
Yeah.
I was giving a little bit too much love to one of the.
Right.
But the award for best binding for energy study it's not been awarded yet. It's still under dispute. And I wanted to nominate you. So, but they insisted that you should still prove yourself worthy. So don't screw it up now. This is important. So, nominee Vidar Aspelin, already in a super young age, he studied the famous key and lock model. It was actually already discussed by the opponent. And it, of course, wasn't an easier version. Right? Very simple models. But can you still do something like this? Like, can you still remember simple prisms, simple polygons? Like, what is this prism called?
What that's called? That geometry.
Yes.
I don't know.
I think Greek.
Greek.
I think Greek.
A pentagon, but that's only for the 5. This is 3-dimensional as well. Okay, pentagon prism. Right. Pentagon prism.
Good. So I also tried to explain for my nomination of Vidar that while he was moving into his department, he actually managed also to rediscover a whole new way of applying thermodynamics, and specifically actually to sofas. So I mean, we actually found that exactly like you, if you make state functions for cushionness is enthalpy, the width is entropy, he actually made a very nice model and explains exactly what you want to choose. So the only thing I'm wondering then is you have to fill the blank, negative enthalpy, positive entropy. For such a process, you would always have, assuming that the process of sitting down or the heat capacity of sitting down is 0,
What would this process be in the bottom left?
Spontaneous. Oh, shit. Spontaneous at low temperatures. So you mean that the left one refers to spontaneous at low temperatures?
That would be the top one.
That's the top one.
Yeah. So what's the bottom left?
Right.
Yeah.
Heat capacity is independent. Did you say that?
We assume that the state functions are temperature independent.
This will depend on the temperature, right? At low temps, so this would be favorable, yes.
For the bottom one.
If it's at low temperature.
Yeah, I mean, it's good enough. It should actually be always spontaneous.
Right, yeah, it's always spontaneous. You're correct, yeah.
I think you're a little bit burned out.
I am.
So, nominee Vidar, I had to explain also, like, you need to be also very important to the community. So I explained to them that the scientific superstar, he's playing music. I don't know if you ever made any music about your work yet, but we'll wait. And of course, also you're basically crushing laws that you others accept for so many times with your interviews. So all in all, you have a great finding, or you have your in-depth knowledge of finding. You have made cutting-edge thermodynamics, and you also have great impact on all your work. So I do think that if anyone deserves anything, you made a little award.
Ooh, nice.
To you.
Wow. It's the Bisque Crown Eater. Thank you so much.
Can you see the confirmation?
This looks a little bit twisted almost, but it's extended one. Yeah.
Everyone in theoretical chemistry, great job.
Thank you.
We're looking forward to see both of the Zoomlink results.
Thank you. Thank you.
Okay, so nothing else always. So with this top line of last top line of questioning, I think we can conclude this, and then there is a few things to note. So for the audience, if you want to stay and see the result for this, you're welcome to the physical chemistry, theoretical chemistry coffee room, which is 2 floors up. And I think if you don't know the way, you will, go along with the crowd, and you will find a way. Of course, for the committee, and we also like with the opponent, we will reconvene in the library upstairs. So I think that you will have to, I guess there's another, is there another link?
Second Zoom link.
So there, you should have a second Zoom link that you can connect to. And then I think considering the time, we just go up and we will reconvene in the upstairs as soon as possible. Okay, so then I think we thank the opponent and the committee, and we thank the respondent Vidar all very much. So, okay, then we meet upstairs.
Yeah.
Okay. There are no participants. Yeah?
Oh.
He was great. It was great.
Hi guys. Hello. Yes. We're heroes. Ja, ja.
Ja, det var lagom för det. Nej, det var chill.
Det var ganska häftigt.
Det var det. Tack så mycket.
Ja.
Känner ni Tack så mycket. Tack. Känner ni kom? Ja, precis.
Have you signed? Have you signed?
Då var det ni kom.
Summering sen.
Ja, precis.
Ja, just det. Sen vi har sett en gång.
Ja, det var en månad.
Vad gör då kanske? Jag tyckte det var på någon Facebook.
Ja, right. Tjena Kalle.
Ja, men jag tror jag...
Tack.
Men det var ju...
Ja, jag vet.
Jag måste springa upp och fixa lite.
Det kändes med dig.
Where did Nantla go now? Yeah, where do you want? Fine. Är du brand ut? Är du färdig?
Ja, det är färdigt. Ja, men då packar jag ihop.
Är det något du vill hjälpa till?
Gärna böckerna.
Ja.
Ja, precis. Det är rätt chill faktiskt. Vänta. Ja, verkligen. Det har varit... Visst, jag tyckte också... Ja, alltså... Det är det, man vet inte. Man känner sig aldrig färdig. Liksom. Det är så här... Ja. Ja. Ja, okej. Jag kan tänka mig att det också är lite mer, kan vara lite mer, alltså humaniora känns också mer som att man har mer olika åsikter på ett sätt. Alltså, ja, men att det kan vara så att folk kan ha sina filosofier och liksom studera det här jättelänge. Ja. Ska vi se. Ja. Ja, det kommer hända nu. Ja, just det, proverna.
Det är precis vad du glömt.
Ja.
Ska jag ta den bara?
Har du?
Jag tar den innan jag är här.
Har du? Ja, jag ska fan.